Hello everyone, good morning, good afternoon and good evening friends from across the globe. Welcome to this session of NAS File System at the SNIA Storage Developer Conference 2020. I am Ankit Mathur and I am Chief Architect with Huawei. Today I will be presenting our work on finding the panacea for extreme performance at high bandwidth and also in high IOPS workload. Since this is a conference in an online format, I would request you to post your questions into the chat box and we can answer those either during the talk over the chat or at the end of the session. First and foremost, the disclaimers. This is an engineer's view of the work and not a marketing document. The features and the performance numbers are indicative and are subject to change since this is a work in progress. So here is the agenda that I have for the talk today. First, I will present before you the background. Then moving on to the state of the art, that is about the work that we have done. And finally, we move on to the performance results. So first and foremost, to get all the non-storage folks up to speed, SAN is a very complex way of deploying compute and storage. It exposes blocks and the layout is tightly coupled with the client. On the other hand, NAS is much simpler to deploy, but brings in a lot of complexity to the storage device. So NAS is exposed to all of the directory consistency, file locking, and other operations that the client operation result in. The metadata operations like lookups, read dir, get attribute, set attribute, create a file, delete a file, rename a file, create directories, all of these land up on the storage device. This is not the case in case of SAN. Also, the large distributed systems don't help the cause here as far as complexity is concerned. And this complexity I refer to the implementer of the NAS storage solution. So starting from the traditional deployments of storage. Traditionally, the NAS storage used to comprise of a single node or a pair of nodes. So the disks would be directly attached, as you can see here, to the NAS box. And what it would expose as a file system would be something that's resident on these disks. So some vendors would actually combine pairs of these storage devices to provide an HA or a high availability pair. The reason for that is all of these are compute or storage devices which have a reasonable chance of failure. So in case this compute network or the storage were to fail, the workload would move to another compute device or another storage device, and the data can be accessed across from another storage node. So since the entire file system is resident on just one location, the metadata operations are really fast. The directories and inodes are co-located, and also the locking semantics can be managed in one location. But it comes with its own downside. The maximum size of a file or a file system that you can get in this particular setup is limited by the amount of disks that are attached on one system. So you could continue scaling up to some extent, but you would finally reach a limit. That is the number of disks that can be attached to a single node, and that's the size of your file system or file finally. Also, as you go on adding capacity, you get silos of multiple such NAS devices, and finally you may find that some of these NAS devices are really highly utilized, running close to 80, 90 or 100%, And there are some others which have spare storage capacity, or they have spare CPU and memory capacities with them. So evolution from here took these devices to another form, wherein these devices were also connected over a backend network, and sort of a pseudo file system was created on top of this. So still this has siloed NAS devices beneath, but there is software that's running on top that would use soft links or hard links between file systems on these to create a view of a global namespace. Also, you would have the ability to receive a request on one node. Let's say we talk about a file that's resident on the storage behind node 3 here, and the client still addresses node 1 for accessing this file. So the node 1 would on the backend network forward this request to the node 3. So you get a feel of you have access to the entire layout from any of the nodes. But still you have limitations of how large your file can be. And also at times when you're working with few large files, let's say 2 large files are present on node 1, and you are not doing IO with any of the files on node 4, you will still have silos of high utilization and low utilization. Also in such distribution, you still have the challenge of how well the layout is distributed. Interestingly, some vendors we found started off from the other end of the spectrum. So they took these storage, created disk stripes, and then on top of that laid out the file system. So there you would have one or more of few file systems which are really high capacity. So you have the ability to expand each file system as and when required, because you could add more storage nodes, and thereby you have the ability to add more disks to it. Also, we found that these kind of layout gave much high bandwidth, especially in sequential IO performance. That is, reads and writes would be really fast. Also, we found that it could give a much better balanced utilization of cluster resources. But what we found is that when you start doing small file operations, metadata operations, and directory operations, they suffer much more. So you could try doing a cache or a copy of these onto multiple nodes, which would reduce your capacity, or you suffer from trying to deal with accessing and coordinating operations across multiple nodes, especially in the scenario of file locking and inode updates. So armed with this information, around 3 years back, when we set out to develop the next generation NAS architecture, we had few requirements in mind already set out for us. We wanted unified file system across our multiple products. So we would have definitely products which cater to really high performance. Then there would be devices that go into the cloud. There would be devices that require lots of capacity for storage, devices that go to the high performance computing world, devices that go to the edge. But having separate file systems for each of them would be an overhead for maintaining and also subsequently adding new features. Next, we definitely wanted performance that should be good for small file scenarios and high IOPS workloads. Also, we liked having good performance for high bandwidth workloads, so that was also in. We wanted our system to be fairly modular and run in the user space. This is because we wanted fault isolation and fault tolerance, and also a fast recovery, because processes in the user space would not bring down the entire system. You would have different modules running in parallel, and each of those would be isolated from faults from other modules. It also gives us the benefit of developing each of the modules separately for specific purpose and combining them together to create different products. We definitely wanted to get the benefit of custom hardware, and also in case of high performance computing world, we wanted it to integrate well into the compute and the whole setup. So now moving on to the hardware architecture. So this is the hardware architecture that we came up with. As you can see here, these are individual controllers, and these 4 controllers that you see here are embedded inside one physical node, or an engine as we call it. Similarly, there is an engine here which again has these 4 controllers. So the controller is individually running the NAS unit, which I will explain later. But these 4 controllers, as you can see, are sharing the front-end module here. They are also sharing the back-end module that talks to the smart disk enclosure. Some of the operations like doing erasure coding and disk reconstruction, we offloaded them to the smart disk enclosure. The smart disk enclosure comes with its own compute, which is ARM based, and it can deal with some of the operations on its own, really without involving the CPU of the controller out here. So the front-end module here can receive the request from multiple clients and make a judgment to forward it to the respective controller which should take up the compute. So this allows for a fairly symmetric setup, and as you can see here that these 2 engines here are connected to the same set of smart disk enclosures. So this allows for failures to be handled fairly smoothly. So you could have a failure on the first controller out here. It could be 2 controller failure, or you could have the entire engine go down, and even then this second engine can take over the workload. So much so that you could also have all of these controllers right from 1 to 7 fail one after the other, and still you can expect the last controller, which is still up and running, to serve the data. Of course, we are not saying that it gives the same performance, but your business can still continue. So this allows for auto balancing, scale out and scale back, and also failover and failback scenarios. So you might start imagining that we have only 8 controller support in our setup. That is not true. Just that this sharing and the failure domains are no longer possible, but over a backend network, you can go on adding another engine and so on. So this is what the hardware architecture is, and I will be talking about some bits of the hardware a little later. Now moving on to the software architecture. So this is where some interesting pieces lie. On the top of this diagram, you see an application running on top of a standard NAS client. You can imagine this to be an NFS client. On the left, you see an application which is running on a private client. So this is that customer who was ready to install a private client provided by us on their end. Below that is the front-end fabric, which you saw the front-end IO module deals with. And below that, on top here are the access modules. This is where we implement the protocol handling. And along with the access module, we also have cache implemented. So this cache can cache data, metadata, directory information, and attributes, access control entries, and so on. The cache here is protected by a delegation system, so it can freely keep the data out here and without worrying about data being modified underneath it by another location. Also, this front-end access module has the capability of talking to the persistence layer directly. So I'll introduce each one of them one by one. Below that, you have the file system being laid out here. But here we have a concept called the FSP, or a file system partition. So the file system is laid out across multiple nodes, split up into FSPs, each one of them responsible for some set of directories and the files within them. Below the FSP, you have a write cache, and below that, you have the index layer. Index layer is basically a database of sorts where you can provide a key like a handle or a file and offset and get where in the persistence the data is stored. So this is effectively an object distribution function. So all of the semantics of a NAS file system end here, and below that is pretty much a key value storage of data. So as I was talking about earlier, if the access node has already retrieved the key where the data lies, it can directly talk to the persistence layer to fetch the data from behind. So it really doesn't need to bother the file system anymore if it's doing a read operation, especially beneficial in large IO operations. Similarly, when you're dealing with write operations, you can commit large chunks of data directly to the persistence layer and just update the file system with the metadata information. The persistence layer behind is basically a highly distributed layout of keys and values. So the access node is basically talking to small chunks of key values spread across multiple nodes. So this allows for the data to be fairly spread across and give a good utilization across the system. Whereas the inode and directory information is isolated and operated in one location. So this allows for faster metadata operations because they are all happening in one location. So if the directory size grows much larger, so there are certain metadata operations that may take a hit, but is sort of expected. That is, if you were to do an ls on a fairly large directory, you can expect it to take more time. So this is where we then decide to split up the directory into smaller bits and spread it across different FSPs. Similarly, when we deal with very large file data, we split that up and span across multiple FSPs. Here you can see that the private client, based on the handle, has information about how the file and directories are laid out and which is the location where they are present. So when it accesses a front-end fabric, it can directly reach that access node, which has the data or the file system ownership for that inode. In case of a standard NAS client, it may end up on different access module, which is not co-located with the file system partition, which is owning the specific file. But specifically in case of large files, once it has the information, the access node can talk to the persistence layer directly, as I mentioned earlier. Below the FSP, you can see that there is a write cache, which is also AI enabled, and it is mirrored across either 2 or 3 locations, depending on the level of protection you expect from the system. Now moving on to the directory distribution. So here you can see a directory layout where you have different directory and file paths created. Like here you have the /a/b, and you have here the /c/c or /c/a, or a /b/a and /abc here. So at the time of creation of a new directory, we use heuristics and create the directory into a new FSP or same FSP. And in the scenario that we end up with lots of hot files in a very large directory, we split the directory across. So I'll be talking about our heuristics for the directory creations in the next slide. So we talked about the two heuristics that we have, which is the local allocation directory layout. What we have seen is that if we make a choice to use the local allocation directory layout, we get almost a 30% higher performance in a multi-client access. In this specific scenario, when a client, let's say this client A, were to access on vnode 0, and it's creating a directory like /a and then creating a /a/b, we would preferentially choose to create these on the node through which this client access is coming. From our studies, we have found that many workloads, the clients do not really stomp over each other's data. And in this specific scenario, if we provide localization of these directories and the files within them to the client from where it is connecting in, you get much higher performance. But you may have a question that in case we go about doing this, soon you may overutilize the vnode 0 on controller A and the controller B vnodes are underutilized. But then a backend process is continuously monitoring the system utilization, both in terms of capacity, that is amount of storage available, and also the utilization of the vnode CPUs. So let's say setting a threshold of 5%, if your utilization from vnode 0 to vnode 1 were to differ by more than 5%, in this scenario, the preference is changed and this client is forced to create the new directories and files on the new vnode, that's the vnode 1 here. So this allows for a good distribution and also a good performance for the clients that are connecting. The next allocation method is the balance allocation directory layout, and this helps us in getting almost 100% storage performance, both in terms of capacity and also other resources on the storage side. So here we try to create recursively a directory path here, /a/b/c and /d. So one client connecting in here, in the balance allocation layout, what we would do is we would force the first creation here, but the next creation goes to another location and subsequently a third location and fourth location. So this may not give you the same performance as before for accessing the files, but this achieves a much better utilization. So as I mentioned earlier, we have machine learning and artificial intelligence running alongside the workloads that would tell which layout works better for us and therefore make an adapt choice. So let's say if we end up with a very large directory and there are lots of hot files inside it. So based on the design we talked about earlier, we would have chosen the directory and created all of the files underneath it. Creating the files underneath the directory in the same location helps really well in especially a read-dir plus kind of scenario. Your metadata operations are really fast because you are dealing with everything in one location. But if the directory itself is fairly large, what do we do? In this specific scenario, what we do is we chop the directory up and split it across. So a directory is nothing but an array of an inode table. So it has information of directory entries, which are basically pointers to inodes. And in scenario that we end up with a very large directory, what we do is we split it up such that the directory is split up as table A, table B, table C, table D. But here we do something smart. When we are pointing to a local inode table and an external inode table, we also create a shadow image of the external inode table. This allows us to avoid transactions for certain operations. As you would be aware that if you are doing a rename or a create or a delete, you might have to coordinate across multiple locations. But with this, you could do the operation locally on the shadow inode table and commit that to persistence locally. And in the background, you could synchronize it back to where the data or metadata actually belongs. And within each of these inode tables, the files are created locally. So the subsequent operations on these files, getting attributes and other things, would be efficient. Definitely, if you're doing a whole reader plus kind of operation on this directory, it might take a hit. But then, as we said, it is a fairly large directory. So anyways, you can expect it to take some amount of performance. And also, in a reader or a reader plus kind of operation, via a cookie-based method, you return only parts of the namespace based on whatever your transaction size is. So recursively, the client has to come back and fetch more information. So anyways, we don't have to fetch the entire directory into one location and return. The subsequent operations are distributed and served from the respective locations. I had talked about the front-end IO module card. So now I talk about in certain more detail what all it gives us. So on the left, you can see a traditional network interface card. So here you have the buffer, IP, TCP, and the driver layer implemented in the kernel. Only the physical and MAC information are operated on by the network interface card. So when an IO comes in, the network interface card reaches out to the kernel. The kernel has to interpret, process the data, and then make an upcall, and then reach the user space. So there was a fair improvement on this front with the TCP offload enabled cards. So here, the implementation on the NIC takes you all the way to the TCP implementation, but still the kernel needs to deal with the buffer and the driver. That means you still need to deal with interrupts, deal with system calls, locks, and threads and switching. So in our hardware, we came up with something called a DTOE. And in the DTOE, you have the implementation all the way to the buffer implemented on the network interface card. And this can directly reach out to the user space. Not only that, the network interface card has an ASIC which can peek into the packets that are received, and looking at file handles, let's say in case of NFS, it can determine where the file actually lies. And based on that, it can schedule the running of this on the right vnode, on the right controller. As you had seen earlier, that within one engine, we share the front-end interface module, and it services multiple controllers behind it. So at least for all of those controllers, the network interface card can decide, do a DMA, push the buffer right into something local to the vnode. And here I can bring up another concept, that is, each of these vnodes are running CPUs, and the CPU would have the NUMA effect. That is, some memory is closer to the CPU and certain other memory will come at much higher latency. And the network interface card, being aware of that, can make an allocation and push the buffer into a location which is right for that vnode and that CPU. Also, since the TCP connection is completely terminating, with the buffer also being handled at the NIC here, in case this user space process or the controller were to fail, the network interface continues to handle the TCP IP, so the TCP IP does not go down, which means in case of NFS and especially in case of SMB, your network continues to stay alive and another controller can take up from there. This gives us much better performance and better reliability. So talking about performance, finally, I move on to our performance numbers. So all of the work that we did over the past 3 years, where has it brought us? So here is a comparison of our performance against another distributed storage device coming from another top vendor. Here we ran the performance on our OceanStore 100D Atlantic platform. This is a highly scaled out platform, and we offer it for our distributed storage where it could have lots of nodes connected. This is really useful for highly sequential workloads, and here we were able to achieve pretty much a number close to the other top vendor. And as I mentioned earlier, this is a work in progress, and these are internal numbers, and this is what we could achieve. So with the single file thread performance, what we see is that we could match the read performance, but also exceed the performance of the top vendor that we compared against in the write performance. So this was the distributed storage setup. We have another product, which is the Dorado, which is a scaled up device. So for really high performance on high IOPS, really low latency, this is the right device for you. So we compared our performance against another top vendor that has really good numbers with high IOPS. We ran different scenarios. So here on the left, you can see the EDA front-end design workload. This run comprises of small file workloads, which are 8K in size and are fairly random, both in terms of creates, reads, and writes. Then the second test we did was the bill image and processing kind of workload. Here the files are fairly small. Here the test used 64 KB files, and we saw multiple random create, overwrites, reads, and in this we compared the performance. Next was the high performance computing world and also the EDA backend design, where we see that the file sizes are large and we see fair amount of sequential workloads here. And finally, we also ran the OLTP workload, which again deals with large files, but in this case, random operations. And the numbers for your perusal are on the right. So we were able to achieve fairly good numbers with our hardware and software design in this architecture. Finally, coming to the conclusions. So what we realized is the best of both worlds is not a far-fetched idea. So with the same architecture, we were able to extend it for the high bandwidth workloads and also extend it to the high IOPS workloads. Also, with AI at our disposal, we could use that for tweaking our caching policies and how we laid out the data on the file system. This helped us to really get much better performance. Also, making use of a modular architecture, we were able to achieve a much quicker turnaround time and faster time to market. And using various modules developed for other products and building up our own custom modules, we were able to assemble it together and create a solution out of it. Also, what we realized is, like you saw earlier, integrating with the front-end module, integrating with how the NUMA of the architecture works for the hardware. So integration with the hardware really holds the key to blazingly, blazingly fast performance. And what we also found is that if customers are fine with it, where we can deploy private clients, you can get even higher performance than the ones listed before, because the private client has information about how the data is laid out. So with that, I conclude my talk. If you have any questions, please post it to the chat and I would be happy to answer those. Thank you so much for your time. And I would also like to take the opportunity to thank SNIA for giving us the opportunity to present our idea in front of you. Thank you so much. Take care and bye.